Hi everyone, how are you doing? Hello Kavya, hi Shweta, hello Devesh, good evening everyone. Hi Shiva, hello Abhinav, good evening. Okay, okay. Viraj Patel is saying your handwriting has become awesome this year. Okay, thank you. So let's get started now. Yes, this recording will be uploaded. Okay, this recording will be uploaded. Good evening, Sonam. So let's get started. So today we are going to start a very new and exciting topic, which is vector space. Okay. So let me just start the topic, which is vector space, and then we will see subspace, basis, dimension, these things, right? Cool. So, by the way, this is not a very new topic in the sense that you know these things already, but it is just that we have not technically discussed them. Okay, technically you might not know it, but you have seen these. I mean, what is a vector space and these things? Okay, already you have seen this. So, for example, let me take an example. Suppose that you have some I mean some coordinate system. Let's suppose in R2. Okay, let's suppose this is R2. So how many dimensions you have in R2? Two dimensions, right? X and Y. You might have already seen this. Okay, this is X, this is Y. Okay, two dimensions you already you have in R2. So this is R2. Now just imagine some vector in R2. For example, let's suppose this is some vector in R2. Okay. For example, this is, let's suppose, 2 comma 3. Okay. And let's suppose there is some other vector in R2, which let's suppose 4 comma something. Okay. 4 comma 2 or something like that, right? Let's suppose these two vectors are there in R2. Now, what are the possible operations that you can do with these two vectors? Maybe you can multiply by some scalar to this vector. Let's suppose you multiply by some scalar which is 2 to this vector. Then what it will become? If you multiply by 2, then it will become 4 6, right? So it will become 4 6. Okay, if you multiply by 2. Now similarly you can do any sort of set of operations between these two vectors also, which means if you want you can add these two vectors. So for example, this is the initial set of vectors that we have, right? And now if you want you can add these two vectors, and you can multiply by some scalar, or there are a lot of operations that you can do. So for example, let's suppose you want to add these two vectors. Now to add these two vectors, what you will do? So you want to add 2 3 and 4 2. So what is the result of 2 3 and 4 2? Adding 2 3 and 4 2, can anyone tell me? It will be 6 and 5. Yes, it will be 6 5. Okay, so it will be 6 5, right? Now 6 5 is some other vector which is also in R2. Tell me, is this an R3? Is this vector in R3? No, right? This is obviously it is also in R2. Now, can you draw the 6 5? Maybe you can try drawing this. Okay. Uh, for example, let's suppose this could be here, somewhere here, right? Okay. So what you can do, you can write 6 5 could be, let's suppose, somewhere here. Then okay, you can draw 6 5 also. Is this fine to everyone? Now this is 6 5, which is also in R2. Okay. So what I'm saying here is that you have two vectors in R2. Okay. And then you did addition of them, and whatever you are getting is also in R2. Is this fine? So let me just tell you what I'm trying to say here is that you started with two vectors. And what are those two vectors? 2 3, 2 3, and 4 2. We started with two vectors, 2 3. Let me also write it. We started with two vectors, 2 3 and 4 2. Right? Now, addition of these two vectors is 6 5, right? Okay. Now, by the way, like it is not necessary, but do you know that how does the addition work geometrically? I mean, that is something that some people study in the 12th class. If you have not studied, then it is not required for gate D. I am just asking you, which means, do you know that this yes, this particular vector, you can write this here, right? You I mean, you can basically shift this vector here. It need not to be drawn from origin, so it is 2 3. You can say something like this. So, for example. Okay. So actually, this is not a perfect diagram, but yeah, you can think like this, that this is 6 5. See, this is 2 3. This is 2 3, and then this vector will be the result of addition of these two vectors. So sorry for the drawing. Maybe I can just draw quickly. Okay. So yeah, something like this. Do you know about it? That you can shift this particular vector here at the head of one of the vector, or maybe you can shift this vector also at the head of this vector, right? So you can do any of them, and then this resultant. So this is 4 3, right? This is, you can say, u, and this is v, and this resultant vector is u plus v. Okay, so this law is called, yeah, parallelogram law. Okay, so you people might have studied this in the 12th class. So even if you have not studied, I'm just asking. Okay, it's fine. If you have not studied, then also it is fine. Okay. Okay. So now let's just move to the definition of vector space. But before I move to the definition of vector space, is this clear that what we are doing here, that we started with the two vectors, which is this and this, and then after addition of these two vectors, we have got the third vector, which is also in R2. Okay. So the this kind of coordinate system that we are currently seeing is basically is R2. Now all of this, whatever we have seen till now, is basically R2, R3, and like this, right? R4, I mean, real spaces, or Rn. So these, all of this is called vector space. I mean, any of this is called vector space. This is also vector space. We will define it technically, but I'm just trying to make some sense here. Okay, this is also called vector space. This is also called vector space. Any of this is a vector space, right? So what is the definition of vector space technically? Is that you have, let's suppose you have some vector space, okay, which is also a set. So basically you can say it is a set of vectors. Vector space is a set of vectors such that, such that, do anyone wants to fill this? Such that what? So see here, if I'm saying that R2 is a set of vectors, okay, which means if this whole thing, whatever vector is here, there are infinitely many vectors, okay, whatever vector is here in this space, I'm calling that set as R2, okay. So R2 I'm calling as a vector space. Why? Because you take any two vectors here, maybe R3, okay, or 4 2, or any two vectors here, and if you add those two vectors, then the resultant vector, whatever you're getting, the resultant vector is also in R2. Okay. So basically, we have taken these two vectors and we added them, and the resultant vector we are getting is also in R2. That's why R2, you can say, is a vector space. So what is a vector space? Vector space is nothing but, you can say, a set of vectors such that if you take any two vectors there, and if you add those, subtract those, or whatever, I mean, the linear combination you want to perform, okay, any linear combination of these two vectors will give you some vector which is also in the same set. For example, okay, for example, just tell me, suppose I just say in this R2, I just say there is a line. Okay, there's a line. This line, is this a vector space? Is this a line? My question is that a line in R2 is a vector space. What do you think? Okay, let's just take any two vectors here. Okay, let's just take any two vectors here. Let's suppose this is something. Maybe this line is. Let's suppose the vector is maybe. Let's suppose okay 1 2. Okay, so this line is k into 1 2, which means I mean this is 1 2 2 4 or k into 1 2. This line is basically the equation of the line. You can understand like this. This is k into 1 2. Okay, suppose now you just take. Okay, suppose this line is k into 1 2. Now you just take two vectors. Okay, any two vectors. Do you want to take any two vectors here? Maybe 1 2. Can anyone suggest me any other vector? Any vector on this line. Okay, you put the value of k and then you will get other vector on this on the same line. So this is 1 2. Maybe you can take one more vector which is 2 4. Okay, is this fine to everyone? Maybe 2 4 3 6 anything. Okay, ठीक है मैं 2 4 ले लेता हूँ. Okay, there are multiple suggestions 2 4 3 6 4 8 something like this. So let's just take two vectors here. Now you add, subtract, whatever you want to do. Just perform the addition. Any linear combination you perform. Okay. This linear combination, if you add them, it will be 3 and 8. Is 3 8 a part of this line? Tell me. Sorry, 3 and 6. I'm sorry about it. It is 3 and 6, right? If you add these two, then it will be 3 and 6. Is 3 6 part of this line? Obviously, yes, right? So 3 6 is a part of this line. Actually, you take any two vectors here. Now, using that law that we have just studied, okay, from that also you can try to understand. That is called parallelogram law. So basically, what does it say? That you have two vectors. Let's suppose this and this you want to add on the same line. Then you will put both of them at sequentially, which means tail of one vector at the head of one vector, other vector. So for example, if these are the two vectors here, this vector from here to here, let's suppose it is 1 2, and this vector from here, from the origin itself, okay, let's suppose it is 2 4. Then you put 1 2 here. Okay, you put 1 2 here. Don't you think you will be getting the same I mean vector on the same line? Are you getting my intuition what I'm trying to say? See, see, you take any two vectors here, whatever is your choice. We can prove it mathematically also. Okay, but for now I just want to show you little geometrically. You take any two vectors here. If you add those two vectors, it will be on the same line, isn't it? Whatever linear combination you want to perform, you do that, it will be on the same line. So if I just ask you whether a line in R2 is a vector space, then what is your answer? The answer is yes. It is a vector space. Okay. Why it is a vector space? Why it is a vector space? Because you take any two vectors here on this line, you perform any linear combination of them, it is on the same line. Yeah, it is passing through origin. So we will talk about the technical definitions later on, but yeah, it is definitely passing through origin. If you put k equal to 0, then 0 0 0 0 0 0 is a part of this particular line. I mean here. Okay, so a line, let's suppose I say a line. Let me also give the definition of the line here, just to be more clear, which is I can say k 1 into 2. Okay, a line in R2, a line k 1 into 2. I mean the equation of the line is k 1 into 2, 1 2 in R2 is a vector space. Then answer is yes. Is this okay? So basically, I'm talking about only this line. Okay, I'm talking about only this line. Tell me, is this line a vector space? Yes. Is this whole thing a vector space? This whole thing R2 is a vector space? Yes. So R2 is also vector space. Line inside the R2 is also vector space. Now tell me, okay, for more clarity, tell me this. Suppose you have this. Let's suppose you have R2 again. Okay. Now, just tell me. We will talk about these things later on, but these are called. I mean, you can say half a space. Okay, half a space means something like this, something like this. Okay. Tell me, is this also vector space? Is this also vector space? What do you think? If it is no, then can you tell me why no? Why this is not a vector space? So I'm asking you, is this is the shaded part is vector space. Just think about it. Okay. So can you give me two vectors linear? If you are saying no, then can you give me two vectors whose linear combination is not as a part of this space? So let me just tell you. See, this is all positive. I mean, x and y both are positive. Here, x is negative and y is positive. So, for example, one of the vector you can take where x is negative. Okay, sorry, x is negative and y is positive. So any vector. Let me just take. Sorry, x is negative and y is positive. So maybe -2 and 3, right? -2 and 3. Okay. And what about this? Here, here you can take any other vector. Maybe for example, this vector. This could be any other vector. Maybe let's suppose it is 4, 2. If you add them, tell me, okay, add or subtract whatever you want to do. Tell me, is there any possibility? Is there any possibility of the linear combination that y becomes negative? Is there any possibility that y becomes negative? Because if y is negative, then I will be here. I will be here. If y is negative, then I will be here. Tell me, is there any possibility if you can add or subtract also? Okay, remember you can do any linear combination, which means cu plus c1u plus c2v. Okay, any linear combination you can do. Just do any linear combination and tell me, is there any possibility that y becomes negative? And the vector, the after linear combination, after the linear combination vector is here. Tell me. Just think about it. Yes. So you can take one vector which is 4, 2 here, and then minus -2 and 3, right? So 4, 2, if you take this vector and then you subtract from here, okay, since this particular dimension is lesser, so if you subtract these two vectors, this particular dimension you will be getting negative, right? Here the negative will come. Okay, here the negative will come. So it is definitely many examples where you can even you can multiply by -1 here, multiply by -1 here, and then you add. Then obviously that particular vector, this is negative, then the particular vector will be here, right? So there are many examples, not just this one. So there are many examples such that you take any vector here, you take any vector here, okay, any vector you can take, any vector you can take here. Let's suppose this is u, this is v. Then c1u plus c2v, can it be here? Yes. How? You can multiply, I mean you can take c1 as -1 and c2 as -1. If you take c1 and c2 as negative, then since y is positive for here also, right? I mean whatever vector you take, this y is positive. So for example, this is, let's suppose, -4, 3. This is, let's suppose, okay, 4, 3. Since y is positive, okay, for both of them, right? Y is positive. So for example, let's suppose it is 4, 5. Any vector, okay? Since y is positive for both of these vectors, now if you multiply by -1, will this y become negative? Tell me. Yes. If you multiply by -1 here, will the y become negative? Yes. And then if you take this kind of linear combination where c1 and c2 are -1, then definitely this particular vector will be here, right? Because y is negative. Maybe like this, maybe like this, right? So what I'm trying to say here is that you started with this space, okay, and then linear combination of these two need not to be in this space. Is this fine? Let me know if that is making sense. So Hers is saying if one of the coefficient is negative, doesn't the vector go out of the vector space? Yeah. So no, one of them means like this y component. If the y component is negative, then it will go out of the vector space. Okay. So basically, what I'm trying to say, that you started with this particular space, and then like we will talk about the the equations of these planes and all. But yeah, you can say that, okay, for now, that you started with this space, and then if you're doing some linear combination such that C1 and C2 both are -1, then you are getting some vector here, right? You are getting some vector here because you are making this negative, you are making this negative, and then if you're adding, then obviously it will be out of this space, right? Since it is out of this space, and that is why you will say this is not a vector space. Getting my point? Okay, let me know little bit if you're getting. See, the things will get clear later on, I mean, in the better way. But for now, are you getting what I'm trying to say? If there is any confusion, then also let me know. Okay, so you are starting with these two vectors. You can take any other vectors also, but whatever you are taking, if you multiply by -1, it will be negative. If you multiply by -1 here, it will be also negative. And then if you add them, definitely it will be here, right? So that's why it is not a vector space. So you can say, finally finally the answer here is this. Is the shaded part the vector space? Then answer is no, right? So let me just go to the next page and let me write the answer is no. Can anyone tell me why? Because the linear combination of all the vectors, I mean, linear combination of any two vectors is not in the same space. So that's why it is not the vector space. Okay. Now let's just take one other example. For example, if I just ask you, is this part, okay, let's just take only this part. Is this part a vector space? Is this a vector space? Okay, just think about it. See, here x and y both are positive, right? X and y both are positive. Obviously, let's suppose 2, 3, or anything, okay? 3, 2. If both are positive, then obviously you multiply by -1, and you add them, it both are negative, right? Then you can definitely have a vector which is here, okay? Or maybe some other combination can lead out of this space. So again, this C1b1 or maybe C1u plus C2b. Okay, if you take C1 as -1 and C2 as -1, then this is not in the same space. Getting? Yeah. So Sonam is giving us one other combination. She is saying that if you take 1, 2 and 2, 3, if you subtract 2, 3, then you are getting -1, right? -1, -1. Then since this is the vector which is not in the same space, that's why it is not a vector space. Okay. So Ankita is saying that, sir, only if both of the y coordinates is multiplied by -1, then no, you can't multiply only the y coordinates or something like that. You have to multiply x coordinate and y coordinate because this is C1 into u, which means both the multiplication should be there. Okay, only both of the y coordinates is multiplied by -1, then it go out of the vector space. But sir, if only one of the y coordinates is multiplied by -1, then it, yeah, it may not go. It is not the case. See, let me just tell you one thing. Okay, let me just ask you one thing. Suppose you are in a village, okay, and let's suppose that you want to prove, okay, you want to prove that in your village it rains daily, and there is someone else in the same village want to prove it does not rain daily. Suppose, okay. Now tell me, Which job is easier? How to prove that it rains daily? You have to show for 366 days or 365, whatever, right? So you have to show for all the days. So if you want to prove that it rains daily, then you have to prove, okay? So prove for 365 days, isn't it? And if someone wants to prove that it doesn't rain daily, then that particular person just need to give, okay, just need to tell one day where it doesn't rain, okay, where it didn't rain. Understood? So this kind of example or this kind of proof is called proof by contradiction or sorry, proof by counter example. So you just proved by counter example, okay? This is called proof by counter example, which means that particular person can give just one counter example and can just destroy the whole argument, isn't it? So if you want to let's suppose disprove something, okay, it is not the thing, okay, then you just need to give one counter example. So similarly here, if you just want to prove that this is not the vector space or want to disprove that that is a vector space, whatever English language you want to use. Okay, so I'm saying that if you want to prove this is not a vector space, just give one counter example. So this is enough. That's all. Okay, this is enough. Let's suppose here this particular person is able to give 360 days example. Is this enough for that particular person? The particular person says that okay, 360 days there is a rain. Obviously not enough, right? The particular person has to prove for 365 days. So similarly, if you are giving me here, if you are giving me that, sir, if we add them, then these are in the same space, it's not enough. Okay, this is not the proof. See, you have to tell for each and every combination. Okay, if there is only one combination, two combination, three combination, the 10 combination doesn't really matter. Okay, so number of the combination or the number of examples doesn't really make your case stronger. Just one counter example can ruin the whole thing. So you are getting the point. So if you want to prove that this is not the vector space, just come up with one of the counter example that okay, if you take these two vectors linear combination, it is not in the same space. That's why it is not the vector space. That's enough. Okay. If you are giving some examples, okay, if you add them, then it is a vector space. No, that's not the proof. Okay, it cannot prove that it is a vector space. To prove, you have to give all the counter all the examples for any two vectors. Okay. So I hope you're getting what I'm trying to say. So here we want to prove that this is not a vector space. So that is why just one counter example is enough. Okay, just one counter example is enough. Okay, to prove that something is not true. I hope you understood, right? Okay. So similarly, like in this case, that here we are saying that if you want to prove for all the days, then here in this case that you can't prove for all the days, right? If you want to prove for all the days, you have to give 365 examples. But if you want to prove just for one day, then just one counter example is enough. Okay. So Abhishek is saying, sir, please keep sharing the weekly schedule. अभी तो गेट डीए में there is no weekly schedule. Okay, so for gate DA there is no weekly schedule. It's just like a live classes. I mean, if there is a recorded, then we will give the weekly schedule. Abhi to as such there is no weekly schedule. Okay, there will be the classes. That's all. I mean, this is the only weekly schedule. Understood? Yeah, except Wednesday there will be the classes. Okay. Yeah, for first 2 weeks we have shared because it was a recorded. It was a recorded session we want to share. That's why we have shared that. Okay, you can watch that. You can watch that. Okay, but now since this is recorded classes, that's why. Oh, sorry, this is live classes. That's why I don't have anything to share here. Okay. Okay. So let's suppose this is R2. Now in this R2, what I'm trying to say here is that this line. Okay, suppose you have one line. Is this line a vector space? This line which is something like this. Is this a vector space? Then the answer is yes. Okay, then the answer is yes. If I just ask you, similarly, if I just ask you, okay, let's suppose one of the quadruple, okay, let's suppose this, is this a vector space? Then the answer is no, right? Okay. I hope you understood these kind of things intuitively. Okay. Little bit you might have understood, but we will see them formally. Okay. So today, whatever we are going to study, I have taken all the screenshots from the Gilbert string. Okay. So once this lecture is over, I will also go through this particular chapter. This is chapter number 3. Okay. Gilbert string, chapter 3. So let's just see their definition of the vector space. So what they are saying, we begin with the most important vector spaces. They are denoted by R1, R2, R3, R4. Each space Rn consists of whole collection of the vectors. Okay, see here. Each space Rn consists of whole collection of the vectors. R5 contains all the column vectors with 5 components. This is called 5-dimensional space. Okay, we will talk about the dimension later on. But yeah. So the definition of the vector space is that the space Rn consists of all the column vectors V with n components. Okay, this is not the definition of vector space. They have defined the Rn. So what is Rn? Rn is a space that contains all the column vectors of V with n components. That's what we already know, right? Okay. The vector space R2 is represented usually by xy plane. Each vector V in R2 has two components. The word space asks us to think all these vectors. So basically, each vector in R2 has two components, right? And R2 contains all the vectors in R all the vectors which is basically of this form, which is having x and y components, right? Okay, let me read some more definitions. So to multiply V by 7, multiply every component by 7. So for example, let's suppose you want to multiply this V by 7, then it will be 7 and 14. So you will be multiplying every component. Here 7 is a scalar. To add vectors in R5, add them components one at a time. You know that how to add or and these things, right? So the two essential vector operations go inside the vector space and they produce the linear combinations. So okay, we will see them. Okay. So we can add any vectors in Rn and we can multiply any vector V by any scalar C. So we have seen that we can add any two vectors, right? And then still the same vector, if it is R2, then obviously since R2 contains all the vectors of this two dimension, right? Two-dimensional vector R2 contains all the vectors. So if you take any two vectors here and if you add them, will the resultant vector be then R2? Tell me. Obviously, yes, right? Because any of this form is in R2. Any of this form is in R2. So if you take any two vectors, then if you add them, it is also in the R2, right? Similarly, if you multiply, let's suppose you take just one vector, and if you multiply that one vector V by C, then the CB is also in R2. If V is in R2, then CB is also in R2, isn't it? Which means let's suppose this 1 2 is in R2, then if you multiply by 7, then obviously दो ही component होंगे ना उसके, तो there is nothing to think here. Okay, I think now they have started building the definition of vector space. So what they're saying, a real vector space is a set of vectors. So it is a set of vectors, right? It is a set of vectors together with the rules for the vector addition and the multiplication by real numbers. So what they're saying is that you have a set of vectors such that okay, there generally are like infinitely many vectors. If it is a line, then the set of vectors are represented like this, right? If it is a line, then set of vector. Let's suppose the line is this. Then you can say this is the set of vectors, right? So if it is a line, then the set of vectors are like this. It is a set of vectors. Is this notation fine to everyone? How many of you know this notation that we write a set like this? Let's suppose I'm writing a set, maybe a set of squares. Okay. So maybe I can say k is a real number. How many of you are familiar with this notation? I think this is called set builder notation, right? Okay. So this is called set builder notation. If you're not familiar, don't worry, we will upload some video and telling you that this is a set. That's how we represent a set. Okay, if you're not familiar with the set builder notation, don't worry about it. For gate CSE, obviously it is in the discrete mathematics, but you don't require to study the set theory. That is for I think 40 hours or 30 hours. You don't need to spend 40 hours just for this notation. It is just very simple. So for example, maybe I can just tell you quickly just in 1 minute for the people who don't know. that we represent a set generally by the curly braces, right? So let's suppose we want to write three numbers. So we can write three numbers like this. Let's suppose we want to write, let's suppose we want to have the set of all real numbers. Then there is actually the notation something like this. Okay. So which is saying that you will be having a set of x where x is a real number. So which means this is same as saying anything. For example, -3, -2, -1. Okay. 0 like this. Okay. So this is same as something like this. So suppose if I say this is k square and k is a real number, then this is same as something like this. Okay. So this is MS, maybe 0, maybe 1, maybe 4, maybe 9, like this, right? So basically, it is a compact way of representing that. Okay, this is how you are representing the set. It is called set builder notation. Anyway, like that's not needed for gate DA. I mean, particularly the set theory is not needed for gate DA. I'm just telling you in short. Those you don't know, we will upload a short video telling you that what is a set, what is a set builder notation, and so on. Okay, we will upload that video later on. Okay. So this is a set where all the vectors in the set are form of k into 1 by 2, 1, 2. So can you give me the example of this set? For example, I mean, can you try to write the set? Maybe you can write, you can multiply by -1. So it will be -1, -2. Maybe you can multiply by 0, right? And something like this. Okay. Something like this. So basically there will be many vectors in this particular set, but I'm just representing like this. Okay. Now let's just come to this definition, what they are trying to say. A real vector space is a set of vectors. So it is a set of vectors basically. For example, R2 is the R2 vector space. Yes, right. R2 is a vector space. R2 is also set of vectors. So this is a vector space. It is also just a set of vectors. Can you tell me the set builder notation in the compact form? Maybe you can write something like this. K1, K2, X, Y, or something like this, right? Where X and Y are real numbers, right? So this is nothing but the compact notation of R2. Is this fine to everyone? Let me know. Okay. So there will be two components X and Y such that X and Y are the real numbers. So this is just a compact notation of R2. Okay. So R2 is also set. I mean, all the vectors of the two dimension is in R2 basically. Okay. So a vector space is a set of vectors together with the rule. Okay. But only the set is only the set enough. For example, this is also the set, right? Where X and Y both are negative. How to represent the set? Maybe you can say something like this. Maybe you can say something like this. Okay. This is also the set. X is less than or equal to 0, Y is less than or equal to 0, right? Okay. So this is also the set. Is the set enough? Is this set a vector space? Is this set a vector space? Then answer is no, right? So just saying that it is a set of vectors, it is not good enough. Okay. So tell me, if I just say a set of vectors is always a vector space, is this true? So a set of vectors, it is not true, right? I mean, there are something that we need to incorporate. Okay. Not just a set. It has to be a set. It is something like, you can say it is necessary, but it is not sufficient. Okay. I mean, it has to be a set, but there has to be something extra also, right? So this is false, right? This is false. The set is not just enough. Okay, we are trying to build the definition of vector space. So if you are not, till now, if you are not understanding the thing, don't worry. We are just trying to build the definition. Once I say that, okay, this particular topic is completed, which means the definition is completed. At that point in time, you can say that, okay, there is some problem or you have not understood. Okay, cool. So what they're saying, yeah, a vector is a set of vectors together with the rules, with some rules. Okay. And what are those rules? For vector addition and the multiplication with real numbers. So there are rules, and the rule says that the addition and the multiplication must produce a vector in the same space or in the same set. Okay. So which we already intuitively understood, which means if you add two vectors, any linear combination of two vectors should be in the same space. For example, if you're interested that okay whether this is a vector space or not, or maybe you take, let's suppose this is space, is this a vector space or not, then you need to check whether any two combination will lead to the same space or not. Okay, so just a set is not enough, you need to check whether any linear combination of two vectors is in the same space or not. Okay, if any linear combination in the same space, then it is a vector space, right? Okay, I hope you understood. Maybe little bit you have understood, right? So now let's just see the formal definition. This is again the intuitive definition only. Okay, so we will see the formal definition. So what they're saying here, that there are actually some 8 conditions that must be satisfied. That is a screenshot from Gilbert Restaurant. So what are those eight conditions? We will see them. But the interesting and the good part is that which is usually not a problem. Which means whatever conditions I'm going to tell you in next 5 minutes, okay, that these are the list of conditions that has to be satisfied by the set. Then actually those list of conditions are very easy to follow. So that's why it is like the Gilbert Einstein himself is saying that it is usually not a problem. Okay, so we will see those 8 conditions, but it is usually not a problem. We will see. Okay, so let's just see those 8 conditions. So basically these are the two mandatory, I mean these are the two conditions which are in the definition. You can have total 10 conditions, and then remaining are the 8 conditions. So I've just listed down the 10 conditions here, right? So these two are the something which we initially started with, कि अगर कि for example कि u and v are in the set v. Okay, u v w are in the set v. So let me start from the beginning. Let v is a set on which two operations, vector addition and scalar multiplication, are defined. If the listed properties are satisfied for every vector in that, or every element in that particular set, and scalar c and d, then v is called a vector space over the real numbers. So basically you take any two vectors, add them, or maybe you take just one of the vector and you take the scalar multiple of that vector. Then also that vector should be in the same space. Okay. And there are some other conditions also. For example, there exists a zero vector. So zero vector must be also the part of vector space always. So tell me in the R2, is the zero vector part of vector space? Is 0 0 part of R2? Does this belong R2? Obviously, yes, right? So this third condition is satisfied for R2. Okay. Tell me the dimension. Oh, sorry, that for example, this is 1 2, let's suppose. Then there's a direction of 1 2, right? So this is a direction of 1 2. Tell me the direction of 0 0. What is the direction of 0 0? It does not have any direction. It is the only vector. Okay, 0 0 is the only vector which does not have any direction. Okay, the only vector which does not have any direction, because there is no magnitude. I mean magnitude is 0. Okay, so anyway, this third condition is actually very easy to check whether zero vector is here or not. And they have also defined the zero vector. Okay, so what is a zero vector? It is just like if you add some vector to it, it should result into the same vector. It is called a zero vector. Okay, is the definition of zero vector clear to everyone? Isn't it very obvious and trivial, just like fifth class thing or 10th class thing, right? Zero means if you add something, that it will be just zero. But for formally we need to define what is a zero vector, right? And now the fourth condition is also very easy to follow. What they're saying, for every vector there exists I mean if you basically have any vector u, then there should be some, you can say, inverse of u or something like minus of u. Okay, I mean that is actually not, they do not need to explicitly specify this, because that is somehow covered using this 2 and 3. Okay, somehow it is covered using this 2 and 3, that c, if you put c equal to -1, it will be minus u. Okay, so what they are saying is that there has to be some vector in the same space such that you add that vector, then you result is 0. Okay, the result is 0. Yeah, that is called additive inverse. Yes. Okay. By the way, these conditions are very easy to follow. That is why we will just narrow down all the conditions into just one thing. Okay, I will tell you that one thing. Okay, all the conditions we will just narrow down into just one thing, because these are very very easy to follow. Okay, this additive, what we said, commutative, right? So we say it, yeah, commutative. So commutative means if you add two vectors either like this, maybe 2 plus 3 or 3 plus 2, it should be same. So I think this is also true for almost every space. This is also true, you add in any order, right? You can multiply like this. So this is also distributive property and these things, right? These things are actually generally true. Do you think these things are hard to follow? That okay, 1 into u is should be, u or something like that. I don't think these are hard to follow, right? CD, I mean CD into U will be like this. So actually, this is not a problem. That's why authors actually doesn't care about these conditions. Okay, although there are conditions, but as the author is saying that which is no problem. And I hope that you must have heard about Gilbert Stein. Who is he? He was actually recently he retired. He was MIT professor. Recently he retired, right? And I think at the age of 88, okay, if I'm correct, at the age of 88, he retired. At the age of 88. So now you can imagine he is most respected professor at MIT. And also, can anyone tell me from, for how many years he has been into MIT, including his, degree of MIT? For how many years can anyone wants to guess? At the age of 22, he joined MIT, I think for his master's or PhD, I don't remember. Okay, at the age of 22, he joined MIT and he retired at age of 88. So he spent his life at MIT, 66 years at MIT. 66 years at MIT. Okay, you imagine 66 years at MIT. Okay. So, by the way, this is not a problem. That's what Gilbert Stein is saying. And for most of the linear algebra, we will be following Gilbert Stein book only. Okay. And also, you have seen the module one, right? In the module one, also I have followed Gilbert Stein. So for all the lectures, I have followed Gilbert Stein, and for the module two also, we will follow Gilbert Stein. Cool. Now let's just see what this paragraph is saying. Okay. Start with the usual three-dimensional space R3. Choose a plane that passes through origin. Okay, I will talk about it in just a minute. So by the way, these conditions are fine, right? So these conditions are also having name. For example, the first thing is called closure. Closure means that it should be closed under the addition, which means if you add two vectors, the addition should be in the, I mean, the resultant vector should be in the same set or same vector space. Okay, this is called closed under scalar multiplication, which means CU is also in V. I mean, these are having names. Obviously, the names are not important, but I'm just telling you these are having names. Okay. Now, I have taken from one of the standard university. I have taken this screenshot. So let's just try to understand this vector space more intuitively. Let's suppose there is two players, two hockey players. This player name is N. Okay, player name. This player name is J. Okay, the player name is N here. Now, whatever way this N is putting his hockey, in whatever way, let's suppose J is putting his hockey. If you take linear combination of these, okay, then if you define any set, all possible ways to hit a hockey puck, then this is also a vector space. Okay, so which means that I mean, I don't know if it will make sense or not, but yeah, I found it some diagrammatic way to tell you, but. Okay, but you may try to relate it. What I'm trying to say is that he's trying to put the hockey in this way. He's trying to put the hockey in this way. So linear combination or maybe addition of these two is basically some vector which is like this. That should be also in the same set, which means you can also put the hockey in this way also. Okay. So if you can put the hockey in this way, then this particular n plus j must be in V. Why? Because V is the all possible ways to hit a hockey puck. So basically, if you can put a hockey in this way, then this is also the part of V. So anyway, like I hope you understood then what they are trying to say. These are the multiple ways. Whatever the ways in which you can put the hockey, it is you can say you can define a vector space out of it. Okay. So maybe we can try solving some questions, and by that you will get more idea that what is a vector space, right? Okay. So just tell me if this is true or false. If V is a vector space, then any equality of the form Ax equal to Bx, where x implies x belongs to V, which means that x is a vector And if you do ax equal to bx, any equality of this form implies that a equal to b. Is this true? It seems true, but actually it is false. What if x equal to 0, right? What if x equal to 0? So 3 into 0 equal to 4 into 0, but it doesn't mean that 3 and 4 are equal, right? So that is why you can say this is false. Okay. I mean, it is little counterintuitive, but this is false actually. I mean, initially we don't think as x equal to 0, but yeah, what if x equal to 0, right? Let's see this particular question. If S is a linearly dependent subset of the vector space V, so they are saying that S is a subset which is linearly independent, then any subset of S is also linearly independent. What do you think? Yes, this is true, right? This is true. Okay. So this was false and this is true. Understood? Let's solve this question. If a vector space V has p linearly independent vectors, then it's impossible for a set of fewer than p vectors to fill V. So suppose this vector space has p linearly independent vectors, then it is impossible for a set of fewer vectors than p to fill that space. What do you think? Yes, obviously this is true, right? For example, you take R3. If it is having three linearly independent vectors, then you can't fill that R3 with just two. So this is true. Let me know how many of you have not understood this. Is this correct? Okay. So for example, R3 has three linearly independent vectors and cannot be filled with two vectors. Actually, there is nothing new in this vector space. You have already been dealt with this vector space, but it is just that name was not there. Okay. At that time name was not there. Okay. Now let's just see this particular thing, what they're trying to say. Is this following a vector space? This is a good question. Do you want to solve this? They've defined some set such that if you do the product of these two sets, I mean these two numbers, it is a positive. Okay. Which means A and B both are positive. Okay. I mean, whatever vectors you have, either A and B both are positive or both are negative. The set of vectors you have here, either both are positive component or both the negative components. Right? Is this possible to have that you take two vectors here, okay, two vectors here, you add them, and you get some vector which is not following this thing that both are positive or both are negative. Maybe one of them is positive and one of them is negative. Is this possible? You're getting my question? What I'm trying to say? That tell me two vectors here. Okay, two vectors here. Okay, first of all, let's just try to understand this. What is this set? Let's first of all try to understand this set, and then we will see the question later on. Okay, let's just first see that what is this set. Tell me the vectors in this set. See, A and B, multiplication of A and B must be positive. Maybe 1, 2. 1, 2 is a good vector. Minus 2, minus 4. I mean, both are negative or both are positive, right? So anything such that both are positive and both are negative. Tell me, is this the vector in the set? Is this minus 1, 2? Is this belonging to W? Tell me, is this belonging to W? No, right? If you multiply these two, then it is not greater than 0, greater than equal to 0. So that's why it is not belonging to W, right? So I hope you understood that what is this set saying. Okay. This is a set of all vectors such that either A and B both are positive or both are negative, because the product must be greater than equal to 0, right? Okay. Cool. And yeah. So now you tell me, Can you have some trick such that you add those two vectors and you get something like one is negative, one is positive? See, if you add them, one is negative. Is it possible to get one is positive? What if there was minus one here? What if there was minus one here? Okay. See, one is negative, one will be positive, isn't it? Yeah. So Sonam has given one example. She is saying that 1, 3 minus 3, 1. It is giving you minus 1 and 2, right? So here, this belongs to W, this also belongs to W, but a linear combination. Okay, you don't need to actually check 10 conditions. You just check the linear combination of these two vectors. Okay, the linear combination is actually not in the set, right? So this is not in W. Understood? So basically, what I'm trying to say here is that you have, I mean, many vectors here. Now, is this possible to add? Okay, to add something. So for example, you have one vector here. You have one vector here. You want addition of them such that one is positive. Let's suppose it is very easy. This is one, two. One is positive. You want one is negative, right? But here, okay, one is positive. Maybe you can have this minus one so that you can have variety. This is one, right? Okay, one is positive. Now you want one of them to be negative. You want negative here. Okay. To get negative here, it's very easy, isn't it? You can have more negative, minus 5 here. You can have just little positive here, maybe one. You can easily have a negative here, right? So this belongs to W. This also belongs to W, but linear combination of them does not belong to W, right? So that is why this W is not a vector space. Understood? So what is the answer? This is not a vector space. Okay. No, for instance, they have given some example. That's fine, right? Okay. So for example, this is in W. This is also in W, but this is not in W. Let me know how many of you have not understood. Okay. How many of you have not understood? If you have understood, it is good. But how many of you have not understood? Just tell me frankly that you have not understood this. Okay, you if you want, you can just rename yourself. Let me just allow you to rename. If you are too hesitate to tell directly, you can just rename yourself, and now you can tell me. Okay, you can rename yourself. Now you can tell me if you have not understood. Okay, okay. So everyone understood, right? Great. Now let's just solve this question. What they are trying to say that consider the set which is in R2 where, okay, the same set they're saying x into y greater than or equal. Okay, the same vector space. I'm sorry, not the vector space, the same space they're having, the same set they're having. Let's just answer this. Does V contain the zero vector? What do you think? This is yes, right? Is V closed under addition? You add two vectors, is this guaranteed to be in V? We have seen that. No, right? We have seen that. Is V closed under scalar multiplication? You multiply by any scalar. What do you think? This is interesting. Yes, it is closed under scalar multiplication. Actually, अगर वो पॉजिटिव है तो ऐसा नहीं हो सकता कि if you multiplying some scalar, it cannot change one to be positive and one to be negative, right? So sorry. So if that is the case, it cannot change one to be positive, one to be negative, basically, right? So either if you multiply minus one, then either both will be negative, which is again okay. If you multiply plus one or plus two or something like that, both will be positive, which is again okay. So it is closed under addition. Okay. Now let's solve this question. This is actually a little tough question. Let me just tell you. I've taken this question from Stony Brook. Let's just try to see that what they are trying to say. Okay. So what they're saying in this particular question, let's just see. They are saying that let V be the vector space over. Actually, till now we have been using the scalars, right? Scalars, you know, right? C, D, these scalars we were using. Those were the real numbers, right? Those were the real numbers. So actually, the vector space is defined over the we call some set of scalars. Okay, so the set of scalars which we were using earlier was the real numbers, but in general it could be anything. Okay, it is a set of scalars. It could be the complex numbers or anything. We will talk about these things later on. For now, you can just take it R, which means the scalars that I'm taking, it is actually the real numbers. Okay. Anyway, so you just take it as R for now. Real number. Okay. Let W1 and W2 as a subspace abhi, okay. Let me first define the subspace and then I will come back to this question. Okay, give me a minute. I will first define the subspace and then I will come to that particular question. Okay. For now, just solve this question. Consider a set V where the this below component they are saying it is greater than or equal to 0, and X they are saying it could be anything. Okay. Let's suppose X belongs to R. So they are saying that in R2 it is a y greater than or equal to 0, it is this much. Okay, they are saying this is the plane they are talking about, the upper half plane. Then V is a vector space. Okay, so what is the answer? It is true or false? This is false, right? We have already seen this, so this is false. Okay, so why that is false? Because we have seen that you can take, I mean, there exist multiple, I mean, there exist two vectors such that you can make them, for example, C1 U plus C2 V. You can take C1 equal to -1, C2 equal to -1, and you can say that okay, the resultant vector will be having negative Y, which is not in the same space, right? I think they are also having some example, maybe here, not closed under. Okay, so anyway, this is false. They are also proving it in some way. Now let's just see one more definition, which is subspace of a vector space. Okay, cool. Let's suppose there's a set. There's a set. Let's suppose the set is S. Okay, it is 1, 2, 3, 4. Can you tell me any subset here? Let's suppose this is U, or maybe this is T. Let's suppose 1, 2, right? So what is a subset? Any element you can take, and then you will say that it is a subset, right? Now, coming to the vector space is also a set, isn't it? So let's suppose there is a vector space, which is obviously a set V equal to something, right? Now, in the vector space, actually, it has to be closed under multiplication, which means the C into V must be in the vector space. So it means C may be 0 also. So 0 vector is also is always the part of vector space. Okay. So 0 is always the part of vector space. And then you can have anything. Okay. So for example, if this is the vector space I define, tell me, is the 0 part of this vector space, this particular space? Yes, if k is 0, then it will be 0, right? So 0 is part of all the vector spaces. Okay, maybe if you want, I can just write it. 0 must be part of. Okay. So let's suppose I have a vector space where I will be having some set of vectors, right? Some set of vectors. Maybe this is 0, 0. There are maybe other vectors. Now I can have subspace of that vector space, subspace. Let's call this subspace as what do you want to call? P, or maybe some other good name. Okay, let's suppose X. Okay, some subspace I want to define over this vector space. So how to define that? It is basically the subset of the vector space. Okay. So if you take the subset here, subset of vector space, then it is a subspace. But there are certain conditions. We will talk about those conditions. For example, for the subset, okay, for the subset, just a subset, is there any condition or that you have to take one, otherwise it will not be subset? Is there any condition for the subset? No, right? There is no condition for the subset. But for the subspace, there is a condition. It has to be subset plus something else also. Actually, it has to be vector space. Okay, it has to be vector space by itself. What is a vector space? Linear combination of any two vectors here also should be in the same space here itself. So again, this is from Gilbert string. A subspace is a vector space. Subspace of a vector space is a set of vectors, including zero, that satisfy two requirements. So basically, the linear combination v plus u or cv has to be in the same space. Okay. So what I'm trying to say here is that it has to be first of all subset. Okay. Subspace of vector space is a set of vectors that satisfy v and u. So basically, first of all, I think they might have written it later on, but I have not taken the screenshot. It has to be subset. And again, any two vectors linear combination must be in the same set. Okay. I mean, it has to be the vector space. Subset plus vector space. Okay. So let's just see this in more detail. So what they're saying, in other words, set of vectors closed under addition, we can leave all linear combination stay in the subspace. Okay. All linear combination stays in the subspace. In short, all the linear combination must stay in the subspace. This is from Gilbert string. We will see more examples. Don't worry. First fact, every subspace contains with zero vector. The plane in R3 has to go through 0, 0, 0. Okay, that is fine. I will talk about it. Now, let's just talk about the subspaces in R3. Okay. let's suppose you have R3, which means there will be three components, right? Now the any subset you take here, how many components the vector will be having? The vectors here will be having. How many components the vectors here will be having? Any subset you take here. Is this the part of the I mean, can you draw this as a subset? I mean, can you have something like this in the subset? No, right? No. So basically here also, any vector, okay, the subspace of R3 has to contain in this form only. Okay, has to contain. So if this is R3, then subspace of R3 will be like this only. Okay. So if I just ask you, like, before I move further, if I just ask you that is is R2 a subspace of R3, then what do you think? What do you think? This is false, right? This is a common misconceptions. People, I mean, not people, actually, the beginner, though, those who just study the vector space, these things, they think that okay, R2 is a subspace of R3. No, actually R3 का subspace होने के लिए at least तीन dimension तो होनी चाहिए, right? There has to be at least three dimensions, and R2 is just a two-dimensional space. So how can R2 be the subspace of R3? So the answer is no, right? R2 is not a subspace of R3. It can never be. Okay. Anyway, let's just define. Let's just see the list of subspaces of R3. Okay. What are the subspaces possible in R3? So actually, for any vector space, there has to be 10 conditions. You might remember, right? But we do not need to again and then checking the 10 conditions. We will be just checking whether zero is there. Okay. We will be just checking two things. Okay. For a quick check, we can just do two things. Zero is in the vector space, and any linear combination. Okay. Actually, you can just say there is just one condition you want to check: cu plus c2v is also in vector space. Is this second condition somehow covering the first condition? Tell me. Is the second condition somehow covering the first condition? Yes or no? The second condition, is this covering the first condition? If C1 and C2 both are 0, then it is covering, right? So actually, we will just check any linear combination, okay, including actually the 0. We do not need to specify explicitly, right? So see, they also many times say that we mention this separately. I mean, the 0 has to be there. We mention it separately for extra emphasis, but it follows directly from the rule to choose C equal to 0, and the rule required 0 into V to be in the subspace. So actually, this 0 vector has to be in the subspace. We should not. I mean, we should not mention it explicitly. It is just for the emphasis purpose. I am saying that 0 has to be in the vector space. But if I just say this, if I just say that, okay, any linear combination has to be in the vector space, then it also cover 0. Okay, 0 has to be in the vector space. But for the extra emphasis, we might say that, okay, 0 has to be in the vector space. But the second rule, okay, this kind of rule also cover that 0 has to be in the vector space. Okay. So anyway, let's just see what are the subspaces of R3. Okay. Tell me, let me start with R2. Tell me, is R2 the subspace? Not a subspace, right? We have already seen this. Okay. Okay. Basically, plane is nothing but linear combination of two vectors. Okay. Plane is actually, you can say it is a linear combination of two vectors, which means you can take two vectors in R3, which are linearly independent. Obviously, if they are linearly dependent, then they will form a, see, if you take three linearly independent and you take every linear combination of this, then it will be what space they will produce? They will produce R3, isn't it? If you take three linearly independent vectors, they will fill the R3, isn't it? So they will fill the R3, which means the kind of, the span or the kind of the vectors they will be covering is actually the whole R3. If you take three linearly independent vectors. Now, if you take two linearly independent vectors, then for example, you take C1U plus C2B. Will this be covering R2? If you take two linearly independent vectors in R3, will this be getting you R2? Tell me. Will this be getting you R2? नहीं, R2 की तो डायमेंशन ही नहीं मैच हो रही ना. So R2 is not answer here. Okay, R2 is not answer here. R2 cannot be the subspace. If you're taking two linearly independent vectors in R3, how it can produce R2? Okay, R2 dimension itself is not matching. Understood? So obviously, no. Just have two components, four vectors, right? Okay. So R2 तो नहीं है, ठीक है. So what does it produce? It actually, we will see the equations later on, but it actually tell you the plane. Okay, it will be a plane in R3. It will be the plane in R3. I cannot visualize this, but let me just maybe try it a little bit. So okay, see here. So there will be the plane. It is hard for me to draw, but there will be a plane in R3, in R3 itself. Okay, there will be a plane in R3. So if you have any two linearly independent in R3, then it will give you a plane in R3. Interestingly, so basically, if you put C1 and C2 both at 0, then it will give you 0 also. So the plane in R3 that it is going to give you, it passes through origin, right? Passes through origin. Okay, because if you put c1 c2 equal to 0, then they will give you 0. So if you have two linearly independents, it will give you the plane. If you have three linearly independents, then it will give you the complete R3. Now if you have for examples of, oh sorry, for example, if you have just one linearly independent in R3, then what it will give you? So someone is asking, sir, isn't the plane on R2 component as well? Then why can't we say that R2 is a subspace? No, basically we will see the projection and all. So okay, there it will be clear, but by the definition it is not the not R2. Okay, by the definition it is not R2 because R2 just have two components, right? We will see the projection and all, and then it might be little more clear after that. So now you tell me, if you just have one linearly independent vector in R3, which means which means just c into u, something like this, then it will give you line in R3. Okay, and not just a random line, that line must pass through origin. Okay, so what is a vector space? Vector space is nothing but a linear combination. Linear combination of vector is called a vector space. If you have multiple, I mean, if you have three, then it will produce R3, which is a vector space. This is a vector space. This is a vector space. This is a vector space. So any linear combination will produce a vector, will produce a vector space, right? So this is a vector space. This is a vector space. This is also the vector space. Now, if I ask you what are the subspaces in R3, then you will say the possible subspaces in R3 is R3 itself. This is the possible subspace in R3. Plane in R3, plane passing through origin, right? This is also the vector, so the subspace in R3. Line passing through origin is also vector space line. Okay. Okay. It will be more clear. But before that, let me ask you one thing. Suppose I have some set V. That set, okay, it will be more clear. Let me just ask you something. Suppose there's a set V something like this which just contains this zero. Tell me, is this V a vector space? What do you think? You take any two, basically there is just one, right? There is just one. Or you take the scalar multiplication of that, you take the linear combination of that only. Okay, whatever you want to do, that stays in this, right? So yes, this is a vector space. Okay, so the answer is yes, it is a vector space. Okay, it is also called as, it is also called as trivial, trivial vector space. Okay, we call it trivial vector space also. So basically, not just R3 is a subspace of R3. I mean, because the by the definition, if there is some set, then you can say the subset also can contain all the elements, right? So basically, if I talk about the subspace of R3, then R3 itself is a subspace of R3. A plane passing through the origin, line passing through the origin, and the last one is zero vector. So these are the possible subspaces of R3. Okay. Any line pass through the origin, any plane pass through the origin, the single vector 0, or the whole space R3. These are the four possible spaces or the subspace of R3. Okay. These are the possible subspace. Yeah. So if the singleton vector is there, then it has to be 0, 0 for the vector space. If you have anything else, then it cannot be the vector space because 0 must be in the vector space, right? Okay. Just tell me, Is this a vector space? Is this a vector space? Yes, zero is there, and any linear combination. Basically, it is just a line, right? It is just a line. So if it is a line, and it might be having three components, which is okay, but any linear combination will give you the vector on the same line. So basically, it is a line passing through origin because it is containing the origin, right? Okay. Just tell me this. Is this a vector space? Is this a vector space? What do you think? Can you get zero? Can you by the addition of these two, by putting any value of k, can you get zero here? No, right? So this is not a vector space because zero is not part of set for any value of k. Okay. No, whatever you put, if we put k equal to 1, it becomes 0. No, how it is becoming 0? K equal to 1, how it is becoming 0? Okay, it cannot be 0 because here it is 1 and it will be 0. 1 plus 0, the first component will always be 1. It cannot be 0. Whatever the value of k you put, it cannot be 0. The first component will always be 1, right? Okay. Just tell me, is this a vector space? The answer is yes, right? Answer is yes. Why? Because it is a linear combination of two vectors. Maybe these two vectors are linearly dependent, linearly independent. Actually, I do not need to care. Either it is a line or it is a plane, right? Either if these are dependent, then it is a line, right? If these are, let's suppose these are the same, okay, the dependent vectors, it will be a line or it is a plane. And line or plane, whatever it is a vector space. So yes, because if both vectors are linearly dependent, then it is a line. If both vectors are linearly independent, then it is a plane. Okay. Passing through origin. Yes. So linear combination of any number of vectors is a vector space. Okay. So linear combination, you can say linear combination of any number of vectors is a vector space. I mean the set which is a linear combination, you can say a set containing all the linear combination, right? is always. Tell me, is this set containing all the linear combinations? Yes, right. K1, K2 can be any real number. Since they can be any real number, that's why it is containing all the linear combination, right? Of the set of vectors. So tell me, is this containing all the linear combination of these two vectors? Are you having liberty to choose any linear combination of this? Any coefficient of this? No, right? You're not having liberty to choose any coefficient of this. So that's why this is not containing set of all linear combinations, right? If you are having actually the vector space is nothing but a linear combination set of vectors. I mean, whatever the linear combination produces, it is a vector space. Okay. Are you getting little bit? Maybe little bit you are getting, but it will be more clear as we proceed. Okay, don't worry. It is a first lecture, so it is just in 1 hour, and it is very new topic for you guys. You might not have heard it or might not have studied it till now, so that's fine. Okay, just trust me. I mean, we will build the subject slowly. Just trust the process, and eventually, in just 1 2 lectures or maybe 2 3 lectures, it will be more clear. Okay, so let's just see this. They are giving the example. So for example one, keep only the vectors xy whose components are positive or zero. This is the quarter plane. So they are saying positive or zero. Okay, x and y. So they are talking about this. This is not a subspace. This is not a subspace and vector space. Both are the same thing. Okay, I mean subspace is just like you can say that the subset of the vector space, but eventually it is also the vector space. Okay, so just see here. Is this a vector space or the subspace? No, right? We have seen this. So they are having this as example one. Example two is in the example two in the Gilbert string. What they are saying is that two quarter planes. So include also the vectors whose components both are negative. So they are saying this one and both are negatives. This one. Okay. This is also, if you take all of this, this is also, they are saying it doesn't make a subspace. You can check this. Okay. If you take this and this as a union, it is not a subspace or the vector space, right? So they have given the example. For example, this one and this one, if you add these two, then you are getting something like this. I think we have seen this. Do you remember this? Do you remember the example of AB greater than equal to zero? Right? They're talking about this only. Okay. I mean, either both are positive, both are negative. This is also not a subspace. Okay. This also doesn't make a vector space or the subspace. So what is the definition of the subspace? A subspace containing U and B must contain all the linear combination. And that's what I just said, right? So this is from again Gilbert-Stein. So all the linear combination of these two vectors is called vector space or subspace. So subspace or vector space. So both are the same thing actually. Okay. So Sonam is saying that she missed whatever I said in last 10 minutes. Okay. Please recall. It is okay. Sonam, is this because of your internet connection? So actually, it was not a great deal. I mean, you can just check these 10 minutes later on. It was not a big thing. Okay, so we will just continue the lecture for 5 or 10 minutes, and later on you can just check that, right? Yes, zero vector is always the part. So tell me, is this containing the zero vector? Okay, zero vector is always the part of vector space. Okay, this is interesting. They are saying there are two vector spaces. Let's suppose U1 and D2. If you take the union of those two vector space, see, I might be interchangingly using the subspace and vector space. This doesn't really matter. Okay. So they're saying that you have two vector space, you have U1 and U2. If you take the union of these two vector space, okay, is this also vector space? What do you think? Let's suppose you have two vector space. For example, let's suppose, let's suppose this is one vector space. Is this a vector space in R2? This line? Is this a vector space in R2? What do you think? Right? R2, if having two components, right? Okay. So suppose, let's suppose this is a line. Okay, sorry, it's not very good diagram, but yeah, let's suppose this is a line in R3. Is this also a vector space? Tell me, right? And line in R3 will be having how many components? Three components, isn't it? Line in R3 will be having three components. Line in R2 will be having two components. Now, suppose there are two lines in R2. Okay, one of them is this, other one is this. There are two lines in R2. Let's suppose there are two lines. I mean, this line could be k into 1 2, or this could be anything else. Maybe y is positive or anything. Okay, x is negative. So minus 1 2, k into minus 1 2. Okay, this line is, let's suppose, this one. This line is, let's suppose, or maybe I do not need to give you the concrete example. That's fine. Okay, the mathematics is not required. You can just understand by the intuition. See, is this a vector space by itself? Okay, just alone. Tell me, just alone, is this a vector space? Yes, right. Let's call it u1. Just alone, is this a vector space? Yes, right. Let's call it u2. Now you take the union of this, which means now one vector here, one vector here. If you take the addition, is this belonging to the union u1 and u2, either u1 or u2? No, right? It may be something like this. Getting my point? So basically, if you are having u1 and u2, which are the subspaces, then the union may not be the subspace or the vector space. Okay, getting my point? So basically, if we are having two vector space, then union need not to be the vector space. See here. Okay, the answer I don't have. So answer is false. Okay, I mean, that is not true. Answer is no. I hope you understood intuitively. Initially, it might seem little counterintuitive, but now it is intuitive, right? You have two vector space u1, you have another vector space u2. Now you take the union, which is u1 u2. Now any two vectors here, linear combination of any two vectors, is this the either on u1? I mean, is this on the u1 union u2? No, right? Avanav is saying union itself means complete space. Union means complete space means, what do you mean to say? So Avanav is saying union itself means complete space. No, no. See, so that's what I'm saying, that initially it might seem counterintuitive, but once you understand that, it will not be the counterintuitive. Okay, I mean, initially for few lectures, maybe for one two lectures, maybe you may seem that okay, the union maybe without thinking, it seems like okay, without thinking, it seems like okay, union is a vector space, but it is actually not. See, let me just explain you once more. Tell me, tell me. So Abhinav, this is not the only set property. The set property is not enough. Okay, subset is not the subspace. उसके साथ भी क्लोजर प्रॉपर्टी सेटिस्फाई होनी चाहिए, राइट? सो फॉर एग्जांपल, लेट्स टेक दिस एज one subspace. Tell me, is this a subspace? Is this okay to everyone? This line is a subspace, right? Okay. Now, is this line also subspace? Both are the subspace by themselves, right? I mean, individually, both are the subspaces or both are the vector spaces, basically. This is, let's suppose, u1, this is, let's suppose, u2. Now, take the union of that. Union means that you include this and include this. Are you including this? Is this the union? What is the union? Union is just this and this, just two lines, right? Just two lines. All the vectors on two lines is just union. Now you tell me, is the union following the closure property? Which means you take one vector here, you take one vector here, you add them. Is this need to be u1 or u2? It may be outside u1 u2, right? So basically union is not this. Union is not this. First of all, you need to understand that, right? Union is this and this individually. Okay. Union is not the complete space. Union is not R2, right? Union means this line and this line. All the vectors on this line, all the vectors on this line is making the union. Now you take one vector here, you take another vector here, you take the linear combination of that, that obviously will be out of either this line or this line, right? So that's why union is not the vector space. Okay. So U1 is a vector space. U2 is a vector space, but U1 union U2 is not a vector space. That's actually one of the very first thing you might be seeing. It means that मतलब later on तो ये 2+2 हो जाएगा कि हाँ मतलब 2+2 4 होता है इस टाइप का हो जाएगा, but initially one of the very first non-intuitive thing that you might be seeing. Okay, so that's why it might be a little tricky, but later on it will be very easy. U1 union U2 is not a vector space. Okay. So just try to understand that this is U1, this is U2. Union is not this. Okay. First of all, you should be clear about it. Union is this and this individually, or all the vectors on this and all the vectors on this, right? And then you take the linear combination of these two vectors. It is not in U1 or not in U2, which means it is not in union. So that's why union is not a vector space. Okay. Okay. There was one question. I think we can go back to that question that I have left. Yeah. So V is a vector space. You can just ignore this. Okay. V is a vector space. And W1 and W2 are the subspace of this. Then what they are saying, prove that, let's suppose that they are saying that W1 plus W2 equal to V and W1 intersection W2 equal to 0. Prove that for any vectors alpha, any vector alpha that is in V, alpha can be written uniquely as alpha 1 plus alpha 2. Okay, so I think this is a little tricky. So we will solve this, after 1 2 classes. Maybe I am not, completely seen that. Okay, for now, like let's just skip this. We will see this after 1 2 classes, right? So anyway, this is not that much tricky. I mean, this is easy only, but still, like I want to make sure that you understand the basic things first. Okay, so that's why I don't want to do this now. Okay, we can do that particular question later on. That's fine. Okay. So now I hope little bit of the vector space is okay to everyone, right? That what is a vector space? So essentially, can anyone tell me in just one line what is a vector space? Just a linear combination of vectors, right? I mean, all linear combination, if you want, you can write like this. Okay. It is obviously, if you are having the linear combination, then it is obviously basically the closed and whatever the property, it automatically follows, right? So for example, zero vector is always the linear in the linear combination. It is closed under addition, or these things are always there, right? Okay. So all the linear combination of vector is called vector space. That's all. Okay. So, for example, in the Gilbert string itself, they've written it so simply. Okay, subspace and the vector space both are the same thing. So they've written it so simply that subspace containing V and W must contain all linear combination in this form, which is CV plus DW. ठीक है? Cool. Now there is a detailed list of properties, but that's fine. Okay, there's a detailed list of properties. Usually those properties are satisfied, so that's why we don't worry about it. I mean, the properties are like this: U plus V equal to V plus U or something like that, right? So the property है वो काफी मतलब obvious सी हैं, तो let's not worry about them. Okay. Okay. Cool. So I think we have covered the vector space definition. So today it was just a definition of vector space, and then we will see this few more definition, which is basis and span. This is also easy definitions. Okay. So for today we can just stop now, and we will be covering these definitions along with the many examples, many questions tomorrow. So tomorrow it will be just a practice questions for basis, span, and these things, right? And vector space. So tomorrow there will be many practice questions after this definition. So for now, we can just stop. If there is any doubt, you can just let me know. Okay. You can just unmute yourself and just let me know the doubt. Yeah, maybe from the today's topic or from the tomorrow's class, whatever the doubt you have, you can just ask me. Let me just enable you to unmute. Yeah, you people can unmute yourself. Okay. Those who are having doubt, they can unmute and ask me.
Sir, this is Tamil here.
Yeah, please tell me.
Sir, yesterday I have a doubt in yesterday's session. There was a question. I'll post the screenshots here as well.
Okay, okay. Ankita is asking, sir, does the union mean entire vector space? No, union just means just like a union of two sets, right? Union means that all the sets here, all the vectors here, all the vectors here. This is what union mean. Okay. Yeah, please
Yeah,
tell
sir.
me.
So there are two. This is one statement where if and only if
Yeah,
linear
just
combination. Yeah.
yeah, sorry. Okay. हाँ बताइए.
Yeah. So the statement says a set of vectors is linearly independent if and only if none of the vectors can be represented as linear combination of other vectors, right? So let's say A is equal to CV plus DW can, if it is represented as that, it is a,
Linearly
so
dependent. So basically, if you can't represent as a linear combination of other vectors, then these are linearly independent.
yes. So let's say an example can be a multiple of other vector instead of linear combination. So in that case, it will become false, right?
Yeah. So yeah, if multiple means there will be just two vectors. You are only talking about two pair of two vectors, right? U and V. So
Let's say we
multiple.
have three. Yes, sir.
Okay, UVW. Yes, tell me.
Yes. Uh, According to this explanation, let's say we can't return U as a linear combination of VW or V as a linear combination of UW or
Okay,
any
okay,
any linear.
okay.
But what if V is a multiple of W?
What is your last line? What is?
What if V is a multiple of W?
Yeah, then also it is a linear combination, right? Multiple of W is also a linear combination. So, for example, V is, let's suppose 2U, then also it is a linear combination of these vectors. I mean, multiple is just a linear combination. I mean, this is just a, one special case where the linear combination is having the zero as a coefficient.
Okay. So so this is that I sent other screenshot as well.
Okay.
In that it says yes, yes. Here in the second statement.
A set of n vectors is linearly independent if and only if none of the vectors are multiple of any other vector. No, none. See, basically, even if they're not multiple of any other vector, then still also, like we have seen this example, like in this particular case, they're not multiple of each other. Any pair is not multiple of each other. Still, they're linearly independent, right? uh Sorry, sorry, they are not multiple of each other. Still they become linearly dependent. So just because they are not multiple of each other, it doesn't mean they are linearly independent. They are dependent. So these three vectors which are here on the screen, they are linearly dependent, even though this condition is satisfied that none of the vector is multiple. I mean, basically when you are saying multiple, it means you're talking about a pair, which means you're talking about U and V, VW or UW. Neither U is a multiple of V nor V is a multiple of W. Neither UW. So basically, none of the pair is a multiple of, in the pair if there are two vectors. None of the there is no pair such that two vectors are multiple of each other, right?
Understood, sir. Understood. So in that example, if it is said that linear combination of other vectors, it also implies that there should be multiples of other vectors, right? According to that question. these are both the same question, but here it is just a multiple of vector. There it is a linear combination of vectors. Both
Yeah.
statements.
Linear combination is a bigger thing. Linear combination means it is a bigger thing. Multiple means it is a you're talking about only two vectors at a time. In the linear
Okay.
combination, you're talking about all the vectors at a time.
Understood, sir. Understood. Yeah.
Okay, you just try to just revise this one more time. Maybe you will get that. Okay.
Sure, sure.
So
Thank you.
this multiple, just to reiterate, this multiple means you are talking about two vectors at a time only. Okay.
Okay, sir. Okay.
Okay. Yeah, this question we will solve in the class. Also, like the solution is available on the gate or flow. You can see just see the solution. I have written the solution for this latest question on the gate or flow. You can see the solution. If there is any problem, we can discuss in the class also. I have already written the solution on the gate or flow. Okay.
Sir, I have one doubt.
Yeah, please tell me.
Sir, I have one question to ask.
हाँ हाँ बताइए.
If V is a non-zero vector of dimension 3 cross 1, then the matrix A is equals to V into V transpose has rank is equals to dash.
Sorry, दोबारा बोलना. If V is a non-zero vector,
Of dimension 3 cross 1,
हाँ.
then the matrix A is equals to
Hmm.
V into V transpose has rank is equals to dash.
This is a class question, right? Have you watched those lectures?
Uh, I've watched lectures, but when I was solving this question, like solution was given different in gate overflow.
Okay, okay. So the rank must be one. The reason is that because here this V and the V transpose, right? If you multiply, it will be a matrix of 3 cross 3, right? Because the dimension is such that it is 3 cross 1, it is 1 cross 3. So the matrix will be 3 cross 3. But here, every vector, so let's suppose it is a V. Every vector here, let's suppose it is also V transpose. Maybe the V transpose, let's suppose
Okay,
V to V.
okay, I got it, I got it.
Yeah, it
Now I
is
have,
V.
yes, at least there will be one, like you
Yeah,
told it in the class.
yeah, right, right.
I
Okay,
got confused due to the solution it was given in gate overflow. It was given differently.
okay, okay, okay. No problem. Okay. So Aditya is asking, sir, I had a doubt. If a m into n, ax equal to 0, if n greater than m, then can a unique solution be possible? X equal to 0, n greater than m, A is a matrix. Let me write here of dimension. You are saying m into n, right? And now you are saying, let's suppose this is 2, this is 3, because n is greater than m. Then the unique solution will be possible. In R2, so these are the two rows and three columns. Yeah, in R2, everything is in R2. Then unique solution possible? Then answer is no, because it must be linearly dependent, right? So since they have to be linearly dependent, then unique solution is not possible. Okay. So let me paste the question also, because in future, if anyone see the slide, they should know that what was the question. Okay. 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 Thank you, everyone. If there is any other doubt, you can just let me know on the Telegram also. Okay. Thank you. Take care. Bye bye.